Hey, my name is Natalie Ivanko, and I'm working as a security engineer at Isovalent. So today I'm going to show you a container escape, assuming a Kubernetes operator or actually a malicious actor has already have access to a namespace where he can create different Kubernetes workloads like pods. And then later I'm going to show you how this malicious actor can actually parse that breakout, which can potentially lead to a whole cluster takedown. But let's take a step back first and talk a little bit about the container escape problem generally on Kubernetes environments. So first of all, security teams can actually protect their Kubernetes environments and their running containers by applying runtime sandboxing mechanisms such as seccomp, Parmor, gvisor, Firecracker. And these tools can actually limit the potential of privilege escalations such as container escape. So what happens during the container escape? During the container escape, an attacker breaks the isolation boundary between the host and the container, and basically he ends up escaping into the host and getting access to all the resources. So these runtime sandboxing mechanism that I mentioned before, they try to defend against this type of attacks, but facing some major challenges. The first problem is that each of these tools offers varying degrees of locking these containers down. And the second is actually the biggest problem that not all the security team has implemented them yet. So how can they verify that these protections can give them sufficient protection against real-world attacks like container escapes? So this is where Cilium and Hubble comes in. Cilium Enterprise provides observing and collecting OS-level process visibility data. So for example, including process binaries, speeds, UIDs, parent binaries, and it actually includes all the full process ancestry going back when actually the pod or the container has started. And it also includes all the Kubernetes identity-aware information, for example, services, labels, namespaces, pods, containers, and so on. So in this way, security teams are actually able to see all the processes that has been executed on their Kubernetes environment, and they can make continuous data-driven decisions to improve their security posture of their system. So security teams can detect if a service which is running in their environment is actually outside of this security posture or not. And then they can capture these process-related events in real time, which is really important in case of, for example, detecting a container escape. So in this demo, we are going to demonstrate an attack on a live cluster in the following way. First, we are going to create a container breakout and reach the host file system. And then as a main step, we are going to create a backdoored container, which is completely invisible for Kubernetes, and it is only managed by kubelet. And then we are going to execute a malware that can compromise the entire cluster. And by doing that, we are going to show that this invisible container can be still detected by Cilium, Hubble, and the superpower of eBPF, even though it is invisible for Kubernetes. So from a demo environment perspective, for simplicity, we are going to use Minikube. And let's assume also that the attacker already has access to the cluster, and then that's what we can see on the top terminal. And then on the same cluster, I have Cilium set up and running, and which monitors all the Kubernetes workload and provide observability, security, and connectivity for them. And for simplicity, I'm going to use Python scripts, which will parse all these JSON events coming from the kernel and are exported to user space via an eBPF program, and which would also look for malicious behavior. So I'm going to run the Python script, which will monitor these malicious behaviors on the left terminal. And then now the first question is, can we get access to the host file system? And here the easiest thing that we can do is just spin up a pod with a privilege equals true flag. This disables all the sandboxing mechanism inside of a pod, and it is enabled by Kubernetes by default. So here is the privilege pod spec. And then we can see the security context privilege true. And then we can see also the name privileged pod. So now let's apply this pod spec. And then let's see if the pod is up and running. All right. So now we have a privileged pod up and running, which give us the same permission as we would have on the node. So why is it so powerful? Because it includes cupnet row and capsysadmin, which is the new root in Linux. And then on the left terminal, we can see that the generated eBPF program was actually able to pick up the new container execution. Here we can see, for example, the namespace, the pod, the actual container, and then the binary which were executed, and also the privileges, capsysadmin, and cupnet row. Now, as a second step, let's use the nsenter command to enter into the host namespace and run the bash command as a host. So here the first flag, actually -t, defines the target namespace where we want to go, and by default on every Linux machine runs a default namespace of 1, which is basically the host. And then the other command line arguments defines the other namespaces where we also want to run. So for example, -m the mount, the -u is actually the user namespace, the -n is networking, the -i is the interprocess communication, and -p is basically the PID namespace. And in the end, we are running bash. So basically, we are breaking out from the container in every possible way, and we are running bash as a host. So now that we are on the host, we can see that the generated eBPF program was able to pick up the malicious events with all the Kubernetes related information. So for example, here we can see that there was a user bean and a center binary detected. We can see that it was actually coming from the privileged pod and the privileged container. And then here we can also see the bash. So now let's go to the etc Kubernetes manifest directory since we have access to all the resources. And then note that if we insert a pod spec here, this is going to be picked up by Kubernetes by default. And if we define a namespace which doesn't exist, the workload will be invisible for the Kubernetes API server. So now let's just insert a pod spec here. And let's call it like totally legit. And then we can see that the name is actually totally innocent container. And then we can see that the namespace has a name doesn't exist, which basically doesn't exist. So now if we run, for example, ps, we can see that the container is up and running. But if we run kubectl pods, we can see that Kubernetes actually doesn't see this container, and this is really dangerous. So now let's pick up the container ID and check if we have any events generated by Cilium and the underlying eBPF program for this container. So let's see if Cilium was able to pick up the container execution. And then now here we can actually see that the container was executed with a bin sh command. And then we can see also the arguments, which is basically an infinite loop. Note that we also see the Docker ID, the PID, the UID as an identification. And note that we don't have Kubernetes identity information since we are outside from Kubernetes. And as a last step, let's just exec into the container. And download the malicious Python script and execute it via pipe. So here we can see that the generated eBPF program was able to pick up the curl connection and actually the Python execution. And here we can see that not only the execution, but also the sensitive socket connection, the network socket connection was detected as well. So here we can see the Docker ID, the PID, the UID, and the binary, and actually the arguments, which were coming from the invisible container. And then here we can see that the sensitive command, which was actually curl and Python, was detected as well from the invisible container.